So I'll just summarize what we did last time. One was so we defined a breakup of the partition function like this. Then we wrote this as so the integral over phi h is done, and this gives you Si lambda and the whole thing, and so the Wilson action S lambda was half phi L defined like this. The second thing we did was, I think I defined two other quantities. One is this. So this was defined as so you integrate out the high energy modes and calculate the generating functional, but there's an IR cutoff because this integral, remember this delta is e to the power of minus p squared by lambda naught squared by p squared. Delta L is, and delta H is delta minus delta L. So it only propagates modes between lambda and lambda naught. So this is a generating functional with an IR cutoff. And it's related to the full generating functional by take the lambda goes to 0 limit and you get back the full thing. And the third thing we defined was this guy, which was the generating functional for the using S. So this was defined as d phi So this is so this is the third object we defined, and this is a useful object because you can use this to calculate the correlation functions of the fields in the using the Wilson action. So that means in doing this calculation you have done the full integral, so you get the full correlation, but there's a scaling factor, and that connection was this. This J is defined here as coupling to phi L is not the same as the J that couples to the original generating functional, and the connection was, you can write e to the w bj, the full generating functional, as this e to the power of w lambda bar with a scaling factor which is delta by delta L j minus half j delta h delta by delta Lj. Okay, so this is a scaling factor. So that means when you calculate correlation functions of the original fields, you will get correlation functions as calculated in this theory modulo that scaling factor. So you get something like this. So this is where as calculated in the S. Okay, so that basically summarizes what we did. So these are the objects of interest. Primarily, these are the objects of interest. Sorry. And what I want to do today, two things. One is to derive a differential equation, RG equation for this one. More precisely, well, for this one and then for this one, and that will turn out to be the famous Polchinski version of the Wilson's RG. So let's do that. Don't need that. So I call this So it starts with this definition. So this thing, where is the lambda dependence of this thing? The lambda dependence, remember this theory is a bare theory defined at a high scale. All the lambda dependence is coming in from here because delta H is delta minus delta L, and delta L has that lambda. Okay, so the entire lambda dependence comes from this. So if you want to calculate the derivative of this, so d by dt, so when I say t now, lambda is like e to the power of minus t, or if you want to be very precise, lambda equals this times lambda naught. So as you progress in time, you're going to the infrared. So d by dt is minus d by d log lambda. So d by dt of this so it's going to differentiate this term. That's the only lambda dependent term. So you get d phi h, bring this down, minus half phi h d by dt of 1 over delta h times the same thing. Now I'm going to compare this with the following object. By the way, I should emphasize that this is all shorthand notation. There are all these integrals over momenta, etc. So this is, I'm neglecting all that. So this is a propagator, so it's a function of p squared typically. So all these terms have to be understood like that. I'm suppressing all that. So let's calculate. So I should be writing functional derivatives, but to save time, I'm just going to write d by d phi and d squared by d phi L squared and so on. So let's calculate d squared by d phi L squared acting on the same thing. Or I'll drop the L index. Okay. So this is equal to, so the phi L is in there. Or maybe I've kept the phi L, so I should call it phi L. So this is d phi h e then acting on this, so this is d squared by d phi L squared e to the power of minus SBI phi L plus phi h. Okay. But because this is a function of phi L plus phi h, I can equally well do d by d phi h squared. So I'm going to make this phi h squared. And now because it's inside an integral, I'm going to integrate by parts and act on this guy. Okay. So this becomes, so when this acts once, you get 1 over delta h times phi h. When it acts twice, you'll get one term with just 1 over delta h, which is field independent, so you don't worry about it. So one term will be just minus 1 by delta h, and the second term will be 2 powers of this. So the second term will be plus phi h 1 over delta h squared. That's the field dependent part. This doesn't play much of a role. Times the full thing. So let's open this up. When you open this up, so this is just phi h 1 over delta h squared phi h. I've just written it out. Compare it with this term. D by dt of delta h is just minus dh dot. Okay. So you can see that, okay, if you forget about this term, this is field independent. Or you can keep track of it if you want, but it's not so important. You see that these two are the same, except there's an extra factor, delta h dot there. Okay, so that gives the equation. No, the entire time t is just lambda. It's a cutoff. That's only occurring inside the propagator. Okay. So what do we get? Half. So the relation between these two is just so this is a minus sign here and a minus sign here. It becomes plus. So in fact, that's why it's a plus sign. Times times, so this is d squared by d phi L squared of that. That's all. So now you can. So let me write it in two different ways. In our old notation, this was e to the power of minus, action was like a wave function. So if you call this psi, or let me for the moment call it psi prime, then this is d squared by d phi l squared is, or if you want to put partials, you can put partials. This one, yeah, this one, because it has no fields in it. It's just a field independent object. It just multiplies the whole thing, some constant. It'll just give you a number, right? It's d phi h of this whole thing. It'll give you something proportional to the wave function, but it's some constant. Yeah, so it'll give you some constant times that, some number times that. Yeah, but it'll be just some overall normalization.
Oh, it's only number, right? Because this SBI is still there, it's a function of L.
No, if you remove this thing is just the wave function itself. So you'll get a constant term here which will just scale the whole wave function by some factor. This wave function is just the partition function. I mean, it's like the e to the power of minus ss. So overall normalization is not important. So this is the equation, and if you can look at it like this, or this is not the way it's conventionally written. It's written in terms of S. So if you write it in terms of S, you get the equation that everyone is familiar with. This is the way actually Polchinski wrote it. And note that, oh, I have a plus sign here, right? Note that delta H dot, because of this minus sign, this doesn't depend on lambda, so delta H dot is minus delta L dot. This has no lambda in it. The lambda is only in there. So I can replace this by delta L dot. So this is minus half delta L dot. And then this is two derivatives, so it's with the plus sign you get this term, and then with the minus sign you get that term. So once again, I keep saying that these are supposed to be functional derivatives, and there's an overall integral over p. So if you want, I'll just write it out to be very precise. So this equation minus half that's the equation. Okay, so this is the way Polchinski wrote this equation, and he used it to prove perturbative renormalizability of the lambda phi 4 theory. Sorry?
Second equation in the box.
Yeah.
That's psi prime.
No, they're all L, psi L. Psi L squared.
Acting on psi.
So this whole thing is psi. Actually, I should say psi prime. I call this psi prime because later on I'm going to define something as psi. But so this is psi prime. It's not a derivative or anything. So that's the equation for S. Now, so I will. Now this equation looks a lot like Schrodinger's equation, and we'll make use of that. So I'm going to use some more simpler notation. So I will call the phi's as x as before. Then this equation indeed looks a lot like this, and I'll call this delta as g. So this is minus. So call it's a Green's function. It's a low energy Green's function. I'll just call it G. So it's easier. Actually, it's easier when you type to type G than to type delta. So I call it G. Minus half G dot. So that's the exact RG in Polchinski's form is just that. So that's very suggestive because you can write down explicitly the integrals and so on. So except for this factor G dot, you can think of this as Schrodinger's equation. Now of course this is the interacting part. So you can combine this. The full action is always the interacting part plus this. This has a well-defined time dependence or lambda dependence. You know what it is. So you can add this and write an equation for S. Okay. I'll just write the answer for that. So I'll erase this. So this is Polchinski's equation for the interacting part. So I'll write down Polchinski's equation for the full S, and that will look a lot like Wilson's equation. So the full S is defined by this object, e to the power of minus half delta L inverse phi squared times e to the power of S I lambda phi. So in that notation, this is e to the power of minus half G inverse x squared minus times psi prime of x. So this is what I call psi prime. So this is psi of x. Actually it's x and t. And the full equation now reads as follows, where psi is now the full thing. So that is the full. So it's a little more complicated, but if you look at your notes for the first lecture, you see it's almost exactly Wilson's equation, except this factor was not there. Wilson had something like this. He had half G dot d by dx times d by dx plus x psi. So modulo this, it's almost exactly the same. And in fact, you can do some change of variables and go from one to the other, which I won't worry about. So very similar to okay, so that's Polchinski's RG. Now for Wilson's RG, I gave you the kernel, the integration kernel. In fact, the whole RG was motivated by that. But it's very easy to write down an integration kernel for this one also. Why? Because this equation we know the answer. So let me do that. So now I will erase this. So that I'll write that equation again. So it's d psi by dt is minus half g dot t squared psi by dx squared. If I just define g as my variable instead of t, this equation becomes d psi by dg okay. In fact, this is a form of Wilson's RG we wrote down in terms of functionals. This is exactly Schrodinger's equation where g is playing the role of time. So we know the answer for this. So psi at xf, call it gf if you want, or tf, doesn't matter, is 1 by square root of something like this, gf minus gi e to the power of minus half xf minus xi squared by gf minus gi. I have to check the sign. I think it's plus. Yeah. Now times dxi times psi xi. So I should call this psi prime because psi prime is just this part. So this is the equation for just this part. I'm not solving this equation, I'm solving that equation. So I call it psi prime xi ti. So gi is the value of g at ti, gf is the value of g at tf. Okay? So in the language of deltas, gi is your initial propagator, so that's what we call delta. And if you want, gf is your final propagator, which is delta L. So here the cutoff is lambda naught, here the cutoff is lambda. And gi minus gf is the difference, is the high energy propagator. And of course you can now convert, put back the p dependence and make this all functional. I mean, in terms of functions, that won't change things. So this is the solution to psi. What about the solution to psi? This is the solution to psi prime. What about the solution to psi? The psi and psi prime are always related, right? Psi of xi and t is just e to the power of minus half xi squared gi inverse psi prime xi t I, and psi xf tf is e to the power of minus half xf squared gf inverse so yeah.
See, the psi that you have written down
Yes.
is supposed to be in the first line actually, here left hand side.
Yeah.
It's just the exponential of the original
Action.
that you started with.
Yes, yes.
Original exponential of original action. In principle, that is should be independent of.
Oh no, psi. So I'm writing down here. I'm writing down an equation for this, right?
Yeah, after putting all this, pairing with this.
Oh, the original SB. Yeah, yes. Psi at initial is this when.
This equation is what
Yeah.
exactly psi is actually. Psi is apart from the definition.
Psi is e to the power of s at any given lambda of phi.
It's a regularized.
No, it's remember what is s of lambda. You start with a bare action at lambda naught, you evolve down, and whatever you get is, so at lambda naught it's your original bare action. That is your initial.
But you are now adding it with the phi lambda.
This kind.
Or this one. This is the S1.
Yeah, this full thing is yes. No, this is just an addition of the kinetic term. That just comes along for the right because we know exactly the t dependence of that. So there's no ambiguity there. All the non-trivial part is the evolution of this.
I'm wondering whether this is a statement of that psi is independent, the total derivative with respect to t is on psi is 0.
Oh, well, since you asked about total derivative of this is definitely 0 because this is the partition function. Yeah, total derivative is 0.
That translates to this equation.
Yes, yes. No, it doesn't. It doesn't translate to this. This. Why is this 0? This is 0 because we assumed for psi we define the evolution of psi in such a way that this is satisfied, and the way we did that was by saying that this is something like g dot d by dx of d by dx plus x psi. So when you put this inside there, it's dx and a ddx. So it's a boundary term, it's 0. So by writing it in this form, evolution as in this form, you're guaranteeing your partition function is invariant. But there's a whole class of things you can write down. So Wilson chose one and Polchinski says, but both of them you notice start with that d by dx. So the partition function is guaranteed to be invariant under this evolution. So the psi, yeah, so the time evolution, so this psi xi is wherever you start your evolution. You could go all the way back to lambda naught, in which case it will give you the bare action you started with, or you can stop anywhere.
Why I'm asking is,
Yeah.
is it connected to renormalization group equation which field theory?
Oh, this is exactly the renormalization group equation. So that's what I said. Polchinski derived. Yeah. So the
Renormalization group equation is also a statement that the integral of this is independent of.
yes. So it is yes.
And then
It's the same thing. So that's why it's called an exact.
It's related to how it's compensated by how phi
changes, right? So here, this tells you how the action should change. Action change means what? The couplings change in such a way that the partition function is invariant. Yeah, so you can derive the beta functions from this.
No, this is denominator.
Yes.
Exactly. What I meant was actually the conventional RG.
Well,
d by dt of partition function is 0, or d by dt of
this is the same thing.
function is 0, and things like that.
Yeah, so starting from, so you could do, see, remember we wrote down a expression for the correlation functions of the theory in terms of the Bayer theory. The right hand side is independent of lambda, the left hand side is superficially has a lambda in it, so that will give you a Reynolds group equation, which you can derive from this also.
So if I start from here, then I can...
You can get those, yeah, definitely, yeah. So, okay, so this is giving me the evolution of psi prime, so I can get the evolution of psi x from this, psi xf tf. I just have to add this to this guy, which is all that. And then psi prime, I will write it psi prime here. I will express it in terms of psi by bringing this to that side and write this as e to the power of half So now I have an evolution equation for psi, the full psi, starting from the Polchinski's equation for the interacting part. And actually, it turns out you can combine these three terms and write it in a more symmetric form. I'll just write the result without doing the algebra. The result is the following. Oops, so yeah, well, I'll just write it and then check. So I think it's like this, xf. This part is the same. Yeah. I will check this. Yeah, this is the final form. Oh, I'll write it in a symmetric form. So there's some factors. 1 minus gf by gi times dxi e to the power of minus half. So you get a nice symmetric form for this, xf by gf minus xi by gi squared so that this evolution for the full psi, so it's a little more complicated than this one, but it's not. It's symmetric. This is the form. Okay. And I want to show you one more thing. All these forms have the same standard form, which is a very useful thing to know. Let me factor out the gf here. I can write this as dxi e to the power of minus half. Let me take out the gf squared, and you can write this as xf minus gf by gi xi squared by 1 by gf minus 1 by gi. And I'll take out one of these gf's and make this 1 minus gf by gi. Okay. So this is of the following form, which we've seen before. This is the form, when we did Wilson's RG, we wrote it in this form. And there was an expression for z and an expression for a. And here you can read off, so z in this case is this, and a is all this. A squared is all this. Okay, and remember that the A contributed to the 2-point function. There was an extra term. What is the role of Z? It just provided a scaling factor for all the correlations. So in this form also you get the same relation between the correlation functions of the Baire theory, the correlation functions of the as calculated from the Wilson action, these factors of Z. And the factors of Z are almost the same actually. If you compare this with that, you'll see that the factors of Z in Wilson's equation and this equation are almost the same. The difference is in this A. So that if I have Wilson, let me remember what was in Wilson's equation. The Z was something like e to the power of minus g. In Wilson's equation we had this function and Z was something like e to the power of minus g, and we chose for g the following form. G was chosen to be some constant t plus p squared by lambda squared or something. So e to the power of minus g has this factor e to the power of minus p squared by lambda squared. Remember what is the role of this? So here what is our factor? It's gf by gi. Gf is e to the power of minus p squared by lambda squared by p squared. Gi is e to the power of minus p squared by lambda naught squared by p squared. Now if you set lambda naught goes to infinity, this is just 1 by p squared, and the ratio gf by gi is just that, which is the same ratio here. Okay? So up to some extra factors, the p dependence is identical in Wilson's form and this form. So what is the function of the Z? Remember what we chose it so that this g was like a time variable, we said, and it has to integrate out the high momentum modes faster than the low momentum modes. That is why we chose it to be a function of like this, and that comes out automatically here, except here that g also has the interpretation of being the propagator. So it plays a double role. G plays the role of the propagator. With the cutoff propagator, it also plays this role of performing the differentiating between the high momentum modes and the low momentum modes. So Polchinski's equation is very similar to Wilson's equation, but it's better for perturbation theory. It's tied to your tied to doing calculations where you keep your kinetic term fixed and just worry about the interactions.
So you choose different regulator for propagator.
Yes.
To start with, when I get
You'll get, yeah.
power of such equation.
Yes. So there's a whole.
What you choose?
No, so you'll get all of them will do the same thing as coarse graining, and they will differ in details. But once you approach some fixed point, universality will take over, and these things won't matter. But in fact, that's one of the things I want to do next is to talk about fixed points, and because this equation is a very general equation, as people are pointing out. What kind of coarse graining you do is not playing much of a role. But if you wanted to go towards some fixed point, you have to choose a certain trajectory in the RG, the space of couplings. You can go in different directions. Okay. So let me talk about that. So okay, so where are we now? So what we've done so far is I started out by motivating this exact RG from Wilson's point of view of integrating out a differential equation that has the property of coarse graining. Then I said the same thing can be looked upon in conventional field theory terms, where you separate your propagator fields into high and low and integrate out things. And this second approach gives you a very similar equation, which is called Polchinski's equation, and that can also be written in the same form as we started out with Wilson's. So that completes that circle of ideas, that the exact RG versus how you integrate out degrees in a functional formalism. Okay? So the next thing I want to talk about is what's going to happen as you proceed to the infrared. What's going to happen to the action? And so that's the topic of fixed points. And I also have to say something about composite operators, because for some of these fixed point equations, you need to define some composite operators. And that's an interesting topic in itself, though I won't have much to say about that. Yeah. No, that's fine. That's okay. Yeah. Right. Yeah.
There are also parameters in the action.
Yes.
Nothing happens to them. They remain as it is. Only the fields get.
No. Oh, I maybe I didn't make it clear. The
So this contains some parameters like coupling and mass.
yeah. So maybe let me write out an S formal form of explicitly and tell you what the RG is doing. Yeah. So when we actually maybe that's a good point. That's a good point to do that. So yeah, so well, but just to answer quickly, the when you write something like ds by dt, what you really mean is this is differentiating the coupling constants. Because so what you have is some phi fourth times lambda, say, in your action. Then what's happening is this lambda is changing with time. So this d phi by dt in this case is just d lambda by dt. But the Wilson action has an infinite number of, and all of them are running. So you may start with a bare theory which has just a lambda, for instance, or maybe a mass. By the time you integrate out fields, you will have an infinite number of couplings. All of them will be determined by this lambda, but they'll flow in a definite way. So it does reduce to your usual beta function equations. The only thing is, in principle, there are an infinite number of couplings that are flowing. But it all starts with the parameters of your bare theory. So I'll say a little bit more about that maybe in a minute. Okay, so what's going to happen as you keep evolving the RG? Well, there are only two possibilities. Either assuming your coupling constants remain in a finite domain and don't go out to infinity, they have to go to some finite point. The other alternative is they keep going in some limit cycles. Now Wilson does mention that possibility, and I believe there are examples where that happens, where you have some angular parameter which keeps evolving and physics is periodic. But those are exceptional situations. The most generic behavior is either it goes out to infinity, goes to 0, or to some fixed point. So now we have to define what exactly do you mean by a fixed point. So fixed point as the word indicates, what the fixed point means is that the action doesn't change form after you do an RG iteration. Okay, but it's not as simple as taking the original action and doing that. You have to write the action written in dimensionless terms. So the action written in dimensionless variables is form invariant. Okay. So what does it mean in dimensionless variables? That means, so dimensionless variables means what? So if you think of a lattice, as you coarse grain the lattice, you have to measure everything in those lattice units, or in terms of lambda, measure in terms of lambda. Okay. So lambda, remember, is your moving scale. It's not your lambda naught. So what you're saying is you take an action, write it in terms of all dimensionless quantities measured in terms of this lambda, in units of lambda, then perform your RG iteration. If you're at a fixed point, the action will look exactly the same, provided, of course, you rescale. So in other words, if you change from lambda to lambda prime, which is lambda by 2, and rescale all fields so that they're in this units now, then everything will look the same. Then the coupling constants of this action, this rescale action, will have the same values as before. Okay, form invariant. So the coupling constants. So the coupling constants now are all dimensionless, because the fields are made dimensionless, the momenta are dimensionless, action is dimensionless, so coupling constant is also dimensionless. So the dimensionless coupling constants have no t dependence. That's what it means to be at a fixed point. So that's the physical idea of a fixed point that you want to implement when you look for a fixed point in this RG. The reason I'm saying all this is fixed point doesn't mean setting this to 0. You have to first rescale, write everything in dimensionless terms, and then the new time derivative has to be set to 0. So let's do that. So what is the rescaling you do? So momentum rescaling is very simple. So you write P as some lambda times P bar. So this is a dimensionless momentum. And the fields you write as phi bar times lambda to whatever the dimension of the field is. So to be more precise, you write phi bar of P. So you're going to write everything. You're going to make this, substitute this with that. This will be dimensionless. So what is d phi? It's the canonical dimension of phi p. Okay, so your action is, so for instance, if your action is d dx d mu phi, then the dimension of phi, the momentum dimension of phi, is easily seen to be d by 2 minus 1. Okay, because 2 powers of this will give you the d to compensate for that, and the minus 2 will compensate for that. Okay? So this is phi of x. So I'll use the square brackets to denote dimension. Of course, phi of p has a different dimension because it's a Fourier transform. So there's an integral over x. So this will have dimension minus d by 2 minus 1. Okay? So you have to keep track of dimensions. So this comes from a d-dimensional x integral which changes by p. So d phi, if you're working in momentum space, will be that. That's the scaling you have to do. Okay, so at a fixed point, these dimensionless couplings remain the same. After you iterate once, you rescale everything, and it has the same value. So as an example, the most interesting example is things that have dimension. So m squared. Let's see what happens to m squared. So m squared, you will, once you write everything in dimensionless terms, so let's see, your action will be, say, d dx m squared, or if you want it in momentum space, it's d dp and you make all these transformations and you write this as d p bar times m bar squared phi bar p bar phi bar minus p bar. Okay, so I've put all the powers of lambda. This is dimensionless, this is dimensionless, this is dimensionless, this is dimensionless. Of course, you can imagine what's the connection between m bar squared and m squared, because you've done it canonically. M squared will be just m bar squared times lambda squared. There has to be. Of course, now ordinarily m squared is a fixed number. Okay, so what this equation says is, so this what this equation says is m bar squared is m squared by lambda squared, right? So that means what it's saying is, if you don't do any, there are no interactions, and you just scale, you start with a given mass. As you lower lambda, your dimensionless mass gets bigger and bigger and bigger. Okay, that's just saying that it's a relevant variable. But if you're at a fixed point, that's not supposed to happen. Your m bar squared is fixed. Okay, so somehow the things have to renormalize your m squared in such a way that this is a fixed number. Okay, so your m squared in fact is a fixed number times lambda squared, and so the physical mass squared is actually going to 0 as lambda goes to 0, in such a way that m bar squared is fixed. So that's what happens at a fixed point. The mass operator phi squared will get will start running in such a way, will start changing in such a way that it compensates this lambda squared and remains fixed. Okay, so that's why fixed points are. It's very hard to get a fixed point when you have a massive theory. You need some strong interactions to modify that. Okay, so now what about the other couplings? So the general action we can write in this way. So what I'm going to do now is to modify the RG equation to write it in terms of dimensionless fields. We'll just modify it a bit. So typically a coupling is of this type, P1 to Pn minus 1. That's the typical term in your action. Yeah. Sorry? No, normally in a massive theory, your m bar squared will be m squared by lambda squared. So as lambda changes, this m bar will change. It's not going to be fixed. It's going to keep increasing, right? So that's a statement that it's a dimension 2 object. Unlike, say, your lambda phi 4, which if you didn't worry about interactions, lambda would remain lambda as you go down. It doesn't have any. This lambda doesn't have any lambda dependence because the dimension is precisely 4 in 4 dimensions. Or this is dimensionless, whereas mass is dimension 2. So to make it dimensionless, I have to make that lambda squared. So m bar is not going to be fixed as you scale lambda, because this product is m. Naively, if you take a free theory, but if you're in an interacting theory, m squared can change due to the interactions in such a way that this thing is fixed. Then you can have a fixed point. Okay. So this is the general form of your coupling. So this you can write as P1 to Pn minus 1. Let me take out the powers of momenta. Let me write it generically as n to m times some products of momenta. Let me. So let me just to be. So sum over m. So this is just very schematic. I'm saying that these couplings in general will have some momentum dependence, and I'm just schematically indicating it by saying, assuming it's a scalar theory, it's a dot product of 2 momenta to some power, and the coefficient of that I'm calling it Vn, comma 2m, and of course you have to sum over all such terms. So generically, these are the pure numbers, and these are the objects that have dimensions. So this will have dimensions to compensate all that in such a way that the whole thing is dimensionless. This entire integral is a part of the action, so it has to be dimensionless. So now if you put in the powers of lambda according to this rule, okay, let's see what happens to your V. So let me do this. I'll do this here. So in terms of dimensionless variables, S, now it's S of phi bar, will be sum over n So first of all, there is this lambda to the power of n minus 1 d. Where did this come from? This came from the momentum integrals. Each momentum integral gives you lambda to the power of d, and there are n minus 1 of them, so that's that. Then you get lambdas from these guys, and that lambda dependence is lambda to the power of n d phi. That's the lambda dependence of that. And then there's lambda dependence coming from here. So I'll write this as 2 powers of lambda. This is lambda squared to that power. So you get lambda to the 4m, 2m. I think I have. Well, there's 1 lambda for each, so I have 4, so I should put 4m there. But this m is the number of momenta. Okay, so here, or actually m2m, this has 2m pairs, so 4m is the number of momenta. So lambda to the power 4m. Okay, times p bar I dot p bar j. I think I should just call it m. Maybe that's a typo. So let me call this m and call this 2m. 2m. Okay. So there are 2m momenta, that's this number, and then this. And this times phi bar, p1 bar, phi bar, p2 bar, phi bar, pn bar. And where's the v? The v is here. V n So this V already has a lambda dependence due to the RG running, but this entire thing is a dimensionless number. Why is it dimensionless? Because everything else is dimensionless. So this better be dimensionless. Okay. So this is dimensionless. So this whole thing is a dimensionless coupling that has to remain fixed at the fixed point. Okay? So we'll call this whole thing as Vn2m bar as a function of all these. And the statement is that at the fixed point, this thing should not depend on t. Okay? So let's write down the connection between the two t dependencies, and you can just check that the following is true. dvn2m by dt. So this is this guy is dv bar to n2m dt plus all this dependence. What is this dependence? N minus 1 d plus 2m plus n d phi times lambda to the power of n minus 1 d plus 2m plus n d phi. Okay. So this time derivative is actually this time derivative plus that, and this is the thing that you want to be equal to 0 at a fixed point. Okay, so the RG running of this should be such that this thing is 0, and then you'll have fixed point. So in my RG, I should, on my left hand side, if I want to keep this time derivative, then all these terms will be put on the right hand side. Okay? So the RG will be written in the following form. So this so let me now. So imagine you're writing ds by dt. At this point I should just tell you what I didn't write down the RG in terms of S. If I can find it. No, I don't have it. Okay, doesn't matter. I just wanted to write the full RG in terms of the full S. Just like I wrote Polchinski's RG, the full RG has extra terms. But anyway, So the Rg as we wrote down there was ds by dt equals something in all those derivatives and all that. So I'll just write it as using some standard notation as, so this is the, whatever Rg you use, Polchinski's Rg or Wilson's Rg, ds by dt equals some functional derivatives on s. This is your right hand side. Now you'll get, if you want this time derivative on the left hand side, you have to compensate for these terms. So our equation becomes ds by, or dt is, so the original Rg had this, so I'm going to write it in terms of this. This will be dv bar by dt plus n plus 1 d plus 2m plus n d phi times this is the left hand side, and the right hand side is just, so I'm just rewriting it in terms of the dimensionless variables. So this part you can write as, say, ds, so I'm just inventing this notation, ds by dt for the dimensionless coupling derivative, and these guys are all, what is this? This is counting, this n is the number of fields in your action. Any term of the action, this counts the number of fields. This counts the number of momenta. So there are basically two terms that you have to compensate, and they're the following. This, I'll write this as minus where minus of all this, n phi d plus n phi d phi plus np. So you can think of this as an operator where this n picks the number of fields that you're acting. So I've written an equation for the particular term labeled by n and m, but when you're acting on a general term, this n counts the number of fields in that term, this counts the number of momenta in that term, and this again counts the number of fields in that term multiplied by the dimension, and finally there's a d. Where does this d come from? Oh, this was n minus 1 d, sorry. There's this extra d. So this whole thing, I've just given it a name. I call it G dilation of S. Why dilation? Because it just comes from the scaling of lambda for purely dimensional reasons. Every term has a certain dimension. When you scale lambda in dimensionless terms, they all get appropriate powers of multiplied by appropriate powers like that, and so this is the dilation term. This is just a sort of a kinematic term. It doesn't have any nothing to do with interactions. Any term with so many n's will have this effect. So we will write your left hand side as this minus that equals the right hand side, and then you can take this to that side, all these terms. So this is all acting on S, by the way. Yeah. So you write your Rg as ds by dt equals G dilation plus GRG acting on S. So this is just a rewriting of the Rg, but in this formulation, when the left hand side is 0, you will be at a fixed point. Okay. This can be called so I'm going to use the word naive fixed point equation. Why naive? Because I haven't talked about, oh, I run out of time. I have to now include the fact that there is anomalous dimension. So far I haven't said anything about that. Okay. So what is I'll just say what is anomalous dimension, and do that quantitatively next time. What is anomalous dimension? You see, we said the fixed point action has to be dimensionless when written in dimensionless terms. But that's not quite true. Why? Because you can always rescale your action. Suppose you have an action, I don't know, half phi box phi plus lambda phi fourth. That's your action. I write phi equals 2 times phi prime. This action will become 2 phi prime box phi prime plus lambda times 16 phi prime fourth. It's the same action. Okay? It's the same action. Physically, there's no physics difference. You can't say if in your fixed point this action becomes that after you do ARG, you can't say I'm not at a fixed point. This is still a fixed point if that is. So you have to, when you define your fixed point, you have to make sure that some normalization convention, it's in some normalization convention, and what we typically say is let's keep the kinetic term fixed with a half. So you have to ensure that you're comparing two actions after the renormalization with the same kinetic term, all in dimensionless unit, the same kinetic term, and then compare the rest of the coupling constants. And then it should not change. But typically what happens when you run this RG is that your kinetic term gets a correction. So half phi p squared phi, so kinetic term, the interactions will modify that. Okay, what will happen? You'll get some term of the form log lambda, some logarithmic divergence times p squared times phi p plus lots of higher derivative terms and all that. This comes from some small p squared expansion. You know, you'll get some function of log of p squared plus m squared by lambda squared, etc. And you expand it, you'll get a correction to your kinetic term, which changes the coefficient to half. So there may be some g squared in front. So your coefficient changes from half to half plus, let me put a half there, g squared log lambda. So as you scale, your thing changes. And typically what happens is, near a fixed point, what happens to your kinetic term is it acquires a factor of, it becomes like this. So as you approach the fixed point, you will find if you just do this procedure, make everything dimensionless, you will get a dimensionless factor multiplying phi which has that form. That means it scales with some power of lambda, but it's a fractional power generally, and you have to get rid of this if you want to see the fixed point. Okay, so this requires a rescaling. That's a famous wave function rescaling that people do when you renormalize. But here that's crucial to see the fixed point nature. So when you write down the RG, you have to build into it the fact that you're going to do this rescaling. And when you do that, you will go nicely to that fixed point. If you choose a different power of eta than what is correct for your fixed point, it will not, RG won't go to a fixed point. It will go somewhere else. Okay? So you have to choose this eta correctly. Only then you will get the fixed point. So it's like an eigenvalue problem. You have to tune your eta to get the thing. So what I'm going to do next time is to modify that fixed point equation to include the effects of this. You get an eigenvalue equation that will fix eta. And then your fixed point equation will be satisfied to all orders. So in order to derive that equation, there are many versions of that equation. The Polchinski version is actually quite convenient. So I have to introduce the notion of what is the operator that does this rescaling. So I'll talk a little bit about composite operators, which is also an interesting topic in itself, and then I'll write down the fixed point equation. And so that will be more or less the last thing I want to do in this course. So write down the fixed point equation. Actual solution of that can be done. It's a little tedious. It's not worth lecturing about. So I'll stop here then.